Hi everyone. Today I'm very glad to have this opportunity to share you with the topic Building and Applications with Python Language in Pyflink. My colleague Dianfu and I will give today's sharing together. Okay, let's start it. This topic will be divided into 4 parts. At the beginning, I will introduce Pyflink generally. Then I will introduce some internals and the designs of Pyflink. After the principal part, my colleague Dan will bring some demos how to build Pyflink application. Finally, we will talk about the future of Pyflink. Okay, let's go on the first part introduction. First of all, let's briefly talk about the mission of Pyflink. It will help us know why we need Pyflink. As we all know, data science and machine learning have two notable features: mass data and computing. Flink, as a stream batch unification computing engine, can meet these two needs. However, as built-in JVM, Flink only supports JVM language natively. It can't support other languages like Python, but Python is one of the most popular languages in data science. It's very hard for data scientists to write Java programs, so it's very important for Flink to support the Python language natively. As for that, we created a module named Pyflink, which means Flink plus Python. Flink has the ability of Python. Now we have already know why we need Pyflink and what the mission Pyflink accomplishes. Next, we will introduce in detail what Pyflink contains. As shown in the figure, Pyflink is divided into two parts. One is the SDK part, the other part is the runtime part. Pyflink SDK gives users the ability to write a Flink job by writing in a Python language. The Python SDK can also be divided into two parts. One is Python Table API SQL. The other one is Python DataStream API. They correspond to table SQL jobs and DataStream jobs, respectively. Regarding the Py4j in the figure, it is a third library which can help map a Python language API to a Java language API, so that we can easily describe the same job to Java jobs through the Python language. Next, let's talk about the role of runtime. As we all know, Flink supports custom user-defined function to extend the ability of API. Similarly, Pyflink supports user-defined Python function for users to meet their customized needs. These user-defined Python functions need to be executed in a Python environment. So the responsibility of the Pyflink runtime is to support a Python environment and execute the Python functions. Now we have a briefly know Pyflink. Next, let's take a closer look at some of the internal design of Pyflink. Firstly, let's take a look at a very simple Pyflink job. At the beginning, we create a string execution environment and read data from a collection, and then we apply custom map function. The map function is a Python lambda function. After that, we submit a job for execution, or use the API like from collection map execute will be transformed to Java APIs through Py4j. Remember it? The tool helps to map Python API to Java API. After watching the Pyflink job, now we will take a look at the Pyflink architecture again. In the previous job, we use the Python DataStream API to declare the job. The job will be transformed to a Java DataStream job. In the job, we define a Python lambda function. This Python lambda function will be translated into a Python operator. The Python operator will help to execute the Python lambda function. Go further, we can take a look at the components of Python operator. Firstly, we know Flink run in JVM, so we need to have a Java operator which is responsible to reading data from upstream Java operator and output results to downstream operator. Then we need a Python worker to execute our Python function. So as shown in the picture, the Java operator have a data service to send the data to Python worker. The Python worker receives the data from the data service and then feed the data as the input arguments to the Python user-defined function to get the results, and then send the results back to the Java operator. The Java operator receives the data from the Python worker and output the results to the downstream operator. As for the state service, we don't let Flink provide state operations on the DataStream API. Okay, next let's think about how to optimize the performance of the Python runtime. First of all, we definitely want less and faster data transmission. Secondly, the data transmission here is closed process, so we need to a progress of serialization and deserialization before data transmission. So we hope faster serialization and deserialization. Thirdly, we hope to have a faster Python user-defined function execution. Finally, we hope maximize CPU utilization rather than that the CPU is idle for a long time. Okay, this is the four major aspects we think about to optimize our Python runtime. Nextly, we will introduce one by one. Firstly, let's talk about less and faster transmission. One common solution is operator fusion. This can help reduce Java operators and Python workers, so that you will have less data transmission. Secondly, we hope the result of serialization is small. So we will support the custom serializer violent general serializer Pico, which used in Python world. The Pico serializer will serialize the type info into the results of the serialization. So another serialization solution is arrow format, which has smaller serialization results. Arrow format is used in Pandas UDFs. About faster data transmission, we choose to send data in batches to get bigger through output. Okay, we can take a look at how operator fusion. As shown in this picture, the job has two map functions and two Java operators. After the optimization, these two Java operators can be merged into one. And then we can eliminate serialization and deserialization over the JVM and the PVM. And the RPC runs serialized trips between JVM and Python VM. This optimization is available for both Python and the Table API. Next, let's take a look at the arrow format optimization for Pandas UDF. The Java operator will convert the input data into error format data, and then send this error format data to Python worker. The Python worker will convert the error format data to Pandas objects. These Pandas objects include Pandas series and Pandas data frame. And then Python worker will put these Pandas series and data frame as input arguments to the Pandas user-defined function. The Pandas user-defined function will execute these function and then put the results to the Python worker. The Python worker will then convert Pandas objects to error format. The error format will be sent back to the Java operator. The Java operator will convert these Pandas error format data to error format data, and then outputs the raw format data to downstream Java operator. Okay, we can find Pandas UDF has two strengths. First is faster data transmission, and the second is it could use high-performance pandas library directly. This optimization is only available in Python Table API. Okay, next we will talk about serialization and deserialization. We create the custom serializers rather than the Pico serializers, which is widely used in Python world. Every type has a dedicated serializer, so you could not serialize the type info into the serialization results. All serializers implementation is powered by Python. From picture, we can see that every type serializer can give 3 times optimization of serialization. Okay. We just talked about the data transmission part. Now, let's take a look at the content of the state service part. As shown in the picture, the state stored ETM and Flink provide a Java implementation of state backend. Of course, we can give a Python state backend and implementation, which can overcome the RPC overhead between JVM and PVM. However, it will give much complexity. About performance, we add many optimizations. For example, we support multi-level read and write caches to reduce the RPC. We add the async write, and we also add lazily read. It can help. We don't need to read all data in map state. Okay, that's all about state service. Next, we can talk about other things. For resource management, we will make multiple operators in the same task node sharing the same Python worker, as shown in the picture. In the left part of the picture, this job has 2 user-defined functions, a map function and a flat map function. This will create 2 Java operator and 2 Python worker. But after optimization, in the picture, in the right part of the picture, these 2 Python workers can be merged into 1 Python worker. Okay, it will reduce the numbers of Python workers. It is good for row-through output jobs. Minimize the number of Python workers needed. For high-through output job, just need to increase the parallelism. Okay. Next, we will talk about the look back mode. It is a very useful feature. As we all know, there will be two Python environments in a Pyflink job. One Python environment is located in client side, which is used to compile the Pyflink job. The other Python environment is executed in remote side. This Python environment is used to execute user-defined Python functions. But in mini-class mode, we can merge these two Python environments. We can execute Python user-defined function in local client Python environment so that we can debug Python user-defined functions in local mode in our IDE PyCharm. It is very useful for debugging. Okay, I have finished my part. The remaining time belongs Dan. Welcome, Dan.
Thanks, Xingbo, for the sharing of the internal design of Pyflink. In the following, I will give two demos of Pyflink to show what does the Pyflink jobs look like, how to write Pyflink jobs, and explore the data with Pyflink in Jupyter Notebook. Before the demo, I will give a quick introduction of myself. I'm an engineer from Alibaba, and I have worked on Pyflink since 2 years ago. Currently, I'm one of the Apache Flink PMC members. Okay, let's start the demo. Let's install the Jupyter Notebook firstly. Let's create a Python virtual environment. Let's activate it. It should be noted that Pyflink only supports Python 3. Here we use Python 3.8. Then let's install a few Python libraries. Here we install the Apache Flink, Jupyter, and NLTK. NLTK is used during the demo. The installation may take a few seconds. Let's wait it. Okay, good. The installation finished. Let's open the Jupyter Notebook. Let's create a new notebook. Here we will show two demos. The first demo is a Python Table API demo. It shows how to compute the word count using Python Table API. Firstly, let's import some commonly used classes. Then let's define the table environment. Table environment is the entry point of Python Table API jobs. Here we create a table environment for a streaming job. Then we needed to define where the data comes from. Here we define a table from a collection of elements. It also supports to define tables which read data from external storage, for example, Kafka, local files or distributed files. Uh, if the table is reading data from external storage, we may want to see what the content is. Let's show the table. We can see that there is one row in the table. However, it contains multiple words in this line. So to compute the word count, we need to firstly to split this line into multiple words. We use a user-defined table function for this purpose. User-defined function could be used to convert one row into multiple rows. So let's execute it. We can see that now we have multiple rows, and each row contains only one word. However, we can see that there are some problems for the word. For example, for this word, it contains both upper and lower cases. The F is uppercase. For this word, the F is lowercase. So we need to do some normalization for the word. Besides, for this word, it contains a period at the end of the word. So we also need to process this case. Firstly, let's convert all the words into lowercase. Then let's remove the punctuation in the word. For example, convert flink to flink by remove the period at the end of the word. Now we can see that all the words are lower cases, and there is no period at the end of the word now. However, there is still one problem. For example, there is stop word. Stop word, for example, is as we know that stop word doesn't make sense in most cases. So here before compute the word count, we will remove the filter words. Here we use a library. We use a library provided your library provided by the NLTK. We check each word. We check whether each word exists in the stop words. If it is a stop word, we remove it. We can see that the stop word has been removed. Now we could compute the word count now. Here we group by the column word and select select the column word and also the counter and also perform a counter aggregation. Counter is a built-in aggregation provided by Flink, so we can use it directly. After when we got the word counter, we could write the result to the external storage. Here we print it to the standard output. We can see that we currently we get the word counter for each word. The word person appears twice, and the word the Pyflink appeared only once. Okay, let's show the next demo. In this demo, we will show how to use state in Python DataStream API. Firstly, let's import some commonly used classes. Similar to the Python Table API, we still need to create a stream execution environment firstly. Stream execution environment is the endpoint for Python DataStream API jobs. Here we create a stream execution environment. Let's set the parallelism for the jobs to 2. It should be noted that even in local deployment, set the parallelism to set the parallelism to multiple parallelism also is meaningful. It means that we will launch multiple Python processes to execute Python user-defined functions. This could help to overcome the global interpreter lock. This is good for performance. Okay. Also, we need to define where the source data comes from. We want to define read data from external storages. For example, Kafka. Here we define a source which from a collection of elements. For each element, it contains 2 columns. Here we could assume that the first column is the username and the second column is the order price. The job is to compute the total order price total order for each user. Let's take a preview for the dataset. Okay, we could see that it contains minus data. So we may want to filter orders which filter rows for the filter the data which the order price is less than 0. Okay, could still take a preview of the data. Okay, we can see that the rows with this kind of rows has been removed. Okay, then let's perform the summation compute. Here we firstly keep by the username. Then we got a kid stream. On the kid stream, we perform this operation. The total, as we know that we need to get all the order for the same user to compute the summation. So here we need to buffer the previous orders. Here we use a value state to for this purpose. The value state is used to store the intermediate result of previously computed the summation of the order. When a new record comes, when a new record comes, we retrieve the previously intermediate result from the state, and then update and plus the current value and update plus it with the current value and update the state. Okay, let's execute it. Then we can see that we get the total order for each user. For Alice, the total order is this value. The total order for Alice, the total order is 143. Okay. Let's see what we want to do in the future for Pyflink. Pyflink is becoming more and more mature after more than 2 years development. However, there are still quite a few areas we need to improve. For example, from the connector side, currently all the table API connectors could be used in Python Table API. However, this is not the same case for Python DataStream API. Currently, only a few DataStream API connectors are supported, as it supposed to convert between Python Table API and Python DataStream API. So even when a connector is still not supported in Python DataStream API, users could work on this by creating a table firstly and then convert it to DataStream. Nevertheless, it would still be great to provide built-in support for all the DataStream API connectors. Another area we need to improve is the checkpoint strategy. It contains two processes for each Python operator, and it will process the elements in a pipeline manner. When performing checkpoint, it needs to trigger to process all the data buffered in the pipeline. This makes the checkpoint time very difficult to predict and causes the checkpoint timeout in certain cases. Besides, we will also spend more time on the usability. For example, adding more metrics to show how many data are buffered in the pipeline. The number of state requests received per second from the Python process. This would be helpful to identify performance bottlenecks. We will also investigate to totally remove the IPC communication. For example, execute Python user-defined functions in the GUM instead of launching a separate Python process. We have already done some prototype, and the performance gain is very promising. We will share the progress and contribute it to the community once we are pretty sure about this. Thank you a lot for listening to this talk.